Hello everyone and welcome to the Autodesk Robot Structural Analysis tutorial brought to you by the Civil Engineering Essentials channel. I hope you enjoy the video. In this video, we are going to start our basically new video series where we are going to use Autodesk Robots in designing and modeling real-life structures. Now the videos you will see here have a slightly different structure than the videos you saw before, because for each structure that I want to model and design, there will be usually at least 3 videos. The first video is basically understanding the drawings and understanding the structure itself. The second video would be about modeling the structure. Of course, modeling could take multiple videos, but in this case, I think it will only take one video. And the third video is usually about designing the structure and producing meaningful reports. Not all reports, but at least producing the reports that are meaningful in Autodesk Robot. Please tell me in the comment section if you kind of like the structure of these videos. And of course, you know that my release schedule is now weekly because like preparing those documents, finding all those resources takes some time. So let's talk about this now. We are going to talk about something called transmission towers, and those are lattice steel structures, which could be assumed to be trusses, but we'll talk about this later when we go to the modeling of those things. Now, the problem that usually a beginner engineer or an intermediate engineer will face, and even sometimes an advanced experienced engineer, is that when he tries to model a new structure to him, he will basically freeze in place for the first, first 10 or 20 minutes, not knowing what to do at all. Well, that is also what happens to me, to be honest. But I have kind of learned how to deal with those structures. Also, the amount of video editing in those videos is going to be minimal because I want you to see my raw thinking process, which could help you, maybe get you some ideas of how to deal with your own structures. Now, this document is from a design report for transmission towers done in Addis Ababa by JICA, which is the Japanese International, I think, Cooperation Agency or something. This is available on the internet. You can actually Google it if you want. I mean, if you just type those, you will. This is a final report. You can actually research this on Google and find this. And I'm going to use this just to make from this report a design problem for you. So the mission is to design a lattice tower for carrying the transmission lines, and of course you need now to apply the forces and be able to model those lattice towers. This is our objective. Now, to do this objective, you need to understand what lattice towers are. You see, there are multiple tower types. There are suspension tower types, and even tension tower types, and ending tower types. The difference between those things is, as you can see, in the type and the way they carry the loads. A suspension tower type, as the name suggests, carries the load off the cable by suspending it, meaning that the weight of the cable is being suspended vertically on the tower. A tension tower type is a tower that carries the loads of the cables in a tension way, meaning that the weight of the cable pulls on the structure and it needs to be accounted for. Of course, there are multiple different types of tension towers. There are also tension towers which have T connections, as you can see here. And finally, there is something called the end tower or dead end. And this is a dangerous task. Those are the most dangerous towers because unlike all other towers, those towers are loaded from one side only, meaning that they feel the tension from one side but have nothing to balance or compensate for the tension felt on one side, meaning that this entire structure will bend in the direction of the loads. So what I'm trying to say here is that those towers are basically feeling tension from one side, as you can see here, and this tension from one side will cause moments on the base of the tower. And now this is a truss, so moments are not carried by members. However, you will have huge tensions. You will have tension forces on those truss members and compression forces on those truss members. So this is a little bit dangerous and you need to take a better look on those. And that's why sometimes you will see in real life some anchoring points here where you anchor your entire structure. This is sometimes happening, that you have anchoring points for the structure to kind of counteract the tension forces that you have here and relieve the structure from carrying all those tension forces themselves by helping it with anchors and cables to anchor them. It depends what you do locally. Anyway, There are also other transmission lines, but this is not part of my video. They are called tubular transmission towers, and this is basically the normal transmission towers you see in everyday life. Of course, you have also those transmission towers which seem strange, and yeah, well, those exist, but that's not the aim of my video. My aim of my video is to use those big things. Now, as an engineer, what would you be provided with? Well, you would be provided with the general shape of the transmission tower, because this is something we usually use, the general shape here. So how would the design problem for you as an engineer look like? Well, for you as an engineer, what will be given to you is the following information. The heights of those transmission lines, like the height of those planes where you are going to connect cables. I will call this plane 1 and plane 2 and plane 3. So the height of those planes will be given. Also, the height of the transmission tower in general will be given. You would think, okay, what about those things? Well, those things might be given, and if they are not given, they follow a usual path. They have a certain profile that we are well acquainted with. You see, we usually like to use those lattice trusses to model those transmission towers, and I will talk about this stuff later when we reach that position and how to model that stuff. Basically, if you don't know what the dimensions are, you can actually check out references, you will find those dimensions. Of course, your mission is to suggest the sections that those trusses should be done using with. So of course the question here becomes, what are the sections that are to be used to resist the loads? Another question you need to answer during your work is, actually, what are those loads? Like, what are you using here? What is the load here? What is the weight dead load? What is the wind load? Is there any other loads I need to take care of? And this is also part of the video I'm going to talk about today. Not the calculation of loads, but at least the definition of the types of loads you need to take into consideration. And also the shape of the tower. So basically this report goes on and shows you the shape of the tower. It even shows you the sections, but I don't want, because it's a design report, so it even shows you the sections, but I don't want to do that. I just want to check out the dimensions of those towers. So if you go on, of course, this is a big project, so it gives you the general, how can I say this, general level of the transmission tower. You can see that it has different heights, and you can see the cables sometimes connect at this +6 meter height, at the +9 meter height, because you have like multiple connection points, so it defines to you where the cable is connected. This is, of course, not your objective. Your objective is not to do this. This will be done for you. Now, there are more drawings for this project that you can look and learn from. However, I want to go to my video-related information. And so this is my goal that I wanted to show in my video today. You see, what you will be provided with is basically the heights of those transmission lines and also maybe the general shape. Now here you have more information, to be honest, and of course you can use this information in future projects for you. This is a good reference that you can use. However, having a larger base or smaller base is something that you have to investigate. It could be provided to you based on local requirements. I'm not really sure about this. It depends on from each country to another country. However, you will have the general shape of the tower, which looks something like this, and it has a big base and a small base here. There is a reason for this. A big base means, because remember, towers might be under moment because it might be under unbalanced loads. So the big base helps those compression and tension elements to produce moment that is required to counteract any moment due to unbalanced loading. So it makes sense to have a larger base in the bottom and a smaller base on top. Now the dimensions here are given, and it depends on your country, but I think the dimensions might be given to you. If it's not, then what will be at least given to you, and this is of course something that will be given to you, is the height of this point on the ground, the height of this point above the ground, the height of this point above the ground, and maybe the height of the tower tip above the ground. Because the design of the longitudinal section or the longitudinal alignment of the transmission cable is a different thing that you will be given with before you start designing your transmission towers themselves. So this should be given, and if it's not, then it means that the longitudinal alignment of the transmission line was not yet designed, so you need to wait for that. So you have those heights, and you have the total height. So this, and this should be inputs to you. Those are things that will be given to you. What may be input to you and may not be input to you is those widths. Those are key factors that might be inputted or given to you and might not. If it's given to you, your job becomes easier. If it's not given to you, then it becomes an iterative process, because you will assume, for example, a base of 5,000 millimeters. design your structure, and then try another structure where the base is 10,000 and design your structure, and then 7,000 millimeters and design your structure. And then, of course, the best structure is the one that is the cheapest to fabricate. As for the shape of the transmission tower, now, first of all, the width here between this line and this line should be known. You should be provided with this because the spacing of transmission lines is something that is provided to you. However, the general shape of the transmission tower is usually this, like we usually use this shape. You can Google any type of shape, just say, for example, transmission tower lattice structures, and you can see all kinds of suggested shapes that you can use. Similarly, in trusses, you had the Howe truss and the Pratt truss and the inverted Pratt truss. So you have a lot of ready truss geometries to use. Okay, so our job might be to find out those widths. However, in this video, I will assume that those widths are given to me. Also, personally, I like my width of the tower to be somewhat equalish to the spacing of the cables, somewhat equalish. But this is only a rule of thumb, because if the tower is really high, then of course my base is going to be much bigger than the spacing of the two cables. But I'm talking about normal height towers. And you can see that actually this design agrees with me. You can see the base is 7 meters or 7,000, whereas the spacing is 7,200 here. So for normal towers, it seems to be the case. But for very high towers, then it doesn't matter what the spacing is because your base will be ginormous. So going on, those are the inputs that I have. Now, the last input I need here is, of course, the loads. And I need not only to know the loads, I need to understand how those loads are defined and what the terminology that is used is in those projects. So to do that, I'll just quickly go to my load table. But before that, I just saw something nice. This project actually has a 3D SketchUp drawing for those towers, which actually will help you make sense of that stuff. However, this is of course not provided to you in normal designs, but since we're talking about this, it's good to mention. You see also that there is something called bird guard, which is the spiky stuff that we put near the high voltage lines, basically to protect the birds, because you don't want to have like, I don't know, like 10 birds dead lying on the ground, because it would be not nice. So there is a bird guard that discourages birds of moving anywhere near close the transmission lines. To understand how to calculate the loads, you need to understand this different jargon, especially the wingspan and the weight span. And to understand this, well, there is a document done by the ASCE itself, ASCE library. And it's called Definitions, Notation, SI Conversion Factors, and you need this for transmission towers. It's about transmission towers here. It talks about all the kinds of definitions, and one of them talks about span, span length, back span, a head span, sag, slack, etc. You can see a nice drawing here. And now you can start looking at the weight span, and you will have a wind span in a moment. So take a look here. You see weight span and you see wind span. Now what I will say right now has nothing to do with the video, but a small piece of advice for your careers. You see, imagine you're an engineer, beginner, intermediate, and even expert, and you get this new job in a new design firm. Of course, even if you are experienced, you do not have experience in all kinds of structure. So when you get thrown a curveball like this, like, hey, let's design a lattice steel structure, or let's design a pre-stressed bridge, or let's design a cable-stayed bridge. Now, sometimes you might be experienced in this, which will not cause any shock effect on you, but you might not be experienced in everything, which would create a shock response in you. You will not say, okay, I have never designed this before, so how can I do that? And this is where my advice comes into play. You see, you have to quickly research and understand the basic terms and use your engineering knowledge to use those terms into your advantage. What I'm trying to say is, I mean, look, it's a structure that is a steel structure. So to design a steel structure, now it doesn't matter what the name of the steel structure is, lattice, tower, whatever tower. To design a steel structure, you know as you experience that you need to know what the loads are and what the dimensions are and any extra design considerations you need to take into account. And this is done by a quick research. You just check out a different design reports, read it, understand it, and whatever terms you find strange, you need to research them. So for example here, let's assume that you found the wingspan and weight span some sort of strange. Now, how would you deal with this? Well, you're not going to give up. So what you do is you start looking up Google and you try look up good references. And you can see that there are guidelines for electrical transmission line structural loading. This is a guideline by the ASCE, the American Society of Civil Engineers, that shows to you how structural loading is calculated. It even assumes to you some gammas and some loads, which is really good. But before I do that, I just want to explain those notations. What is a weight span? What is a wind span? Now, there is some English here, but I want to make it as simple as possible. Now, you would think weight span, wind span, aren't they equal? Well, let's talk about this very quickly. Imagine that you have tower number 1, and you have tower number 2, and you have tower number 3. Now, between those 3 towers, there is a transmission line, one singular transmission line, moving from tower to tower, as you can see, being suspended by all those towers. So you have a distance between the towers. Let's say, for the sake of argument, that this distance here is 500 meters, and the distance here is 500 meters. Those are big transmission towers, by the way. So far, so good. Now, the weight that this transmission tower should resist, I mean, you would think that this transmission tower feels half the weight of this cable and half the weight of this cable. So if you have the length of this cable, or half the length of it, so half the length of the cable from the left side and half the length of the cable from the right side is what this tower will feel. And you would basically say rho multiplied, rho which is the density, multiplied by area, multiplied by length over 2, plus rho multiplied by area, multiplied by length over 2, is what this tower feels. And you're perfectly correct with this. However, this only works if you are dealing with a totally flat terrain. Because in reality, your transmission towers do not work on flat terrains. Your transmission towers might be on sloped terrain. Like, let's say that you have a valley like this, and you have a transmission tower, I'm zooming out now, here, a transmission tower here, and a transmission tower here. And now the lines go like this. Of course, this is now an exaggeration, but just bear in mind with me. This is now, of course, an exaggeration. Also, it's a safety violation because you cannot have high voltage cables so close to the ground, so you need a tower here. But now bear with me, just like close an eye for all those violations I'm doing right now. So you have those cables now. Now, using what we've just learned, if you say that it's 500, 500, you would think that you take half the cable here and half the cable here. No, this is not correct. You see, this tower will feel more tension than this tower because it's in the valley. Usually the towers on top will feel more tension than the towers on bottom. But okay, how do I know this? There is something called the point of sag, which is the point where you reach the lowest altitude before the cable starts rising again. This is called the point of sag. And we use the point of sag to find the tributary length of cable that this tower carries. So let me just draw again for you a better shape to understand. So, okay. So you can see that you can easily detect the point of sag. This is the point of sag, and this is the point of sag, meaning that this tower is responsible for this length and this length, whereas this tower is responsible for all this length and, of course, whatever is on the right side, but I didn't draw it. Which means that the weight span is not just simply the distance over 2, it's the distance over 2, or at least, I mean, it's not simply the length of the cable over 2, it's the length of the cable over 2 if it's a perfect flat ground. However, we are not dealing with flat grounds, so it's not distance over 2. However, according to the ASCE guidelines, the weight span is the distance between the lowest point of sag in both spans. If you look here, you have the lowest point of sag here, you have the lowest point of sag here, meaning that this structure is now responsible for this weight span. And this structure is responsible for more weight span because obviously it has a longer span on the right side. And now here a problem arises, and that's why you need the input of the surveying team to recommend to you those parameters. You see, this is a weight span 700 meters, but I just told you that the weight span is actually not equal, and it will change with the terrain because you could have a terrain. Remember, those are transmission lines; they span a lot of terrain. So you could have a terrain that looks like this. And the problem with this terrain is that the spans change depending on something called the back span and the forespan. The back span is a span before, the forespan is a span after. So since those things change, you need the input of your surveying team or your own input. Like, you need to know the longitudinal distances that you are going to cover with your cables. And this might be given to you or this might be something you will have to do. If it's given to you, then perfect. If it's not given to you, then you have to do it yourself. Also notice that this span is different than this span. So each tower has its own span. Now you cannot design each tower alone because it will take a lot of time. That's why you have a recommendation for the width span that should be on the conservative side. What about the wingspan? Well, the wind span based on the ASCE is simply the average of two spans because wind doesn't care about how the cables are. We just assume that wind is half this span plus half this span. You say it says it's the mathematical average between backspan and forespan, and this is used to calculate the wind loads. The last point I want to cover is okay, assuming that you do not have a recommendation for those spans, how would you do that? This actually takes some time, but you would need the longitudinal profile of the towers to see the spans and try to predict a safe weight span to be used. Of course, if you have drastically different spans, you might design two towers, one for small spans and one for big spans. Also notice in this project, the minimum clearing spacing was 30 meters. You can see that in this position, the minimum clearing distance was achieved, 13-meter distance separation between the cable and anything that is close to the ground. And I've mentioned that there is a minimum distance requirement, a clearing distance between the cable and the ground. It depends on the voltage of the current that runs in the cable. Now, I'm not an electrical engineer, so the electrical engineer is who decides exactly what is happening here. So yeah, that's it. I think I covered everything relating the understanding of those structures, because next time we will use this understanding in modeling the structure and modeling its forces, and then we are going to use everything to wrap it up and design the structure. So yes, I hope that this new format and style of video delivery makes sense to you, and I hope that you enjoyed the video. Stay tuned for part 2 of this, where we model the structure, and part 3 of this, where we design the structure. If you kind of liked the video, then of course please like, share, subscribe, and comment. It helps a lot. As per usual, this is the Civil Engineering Essentials channel, and we will catch you in the next video.